The skin effect is one of the most fundamental concepts to master in microwave engineering. When you transition from designing low-frequency circuits to high-frequency microwave systems, you can no longer assume that current flows uniformly through the entire cross-section of a wire or a trace. At microwave frequencies, the current is forced to flow almost entirely in a microscopic layer at the very surface of the conductor. This active outer layer is known as the skin depth. Here is a deep dive into the conceptual physics, the underlying theory, and the exact mathematical calculations for standard microwave materials.
Conceptual explanation. Why does current move to the surface? To understand the skin effect conceptually, imagine electrons flowing through a solid copper wire. If the current is direct current, or DC, the electrons flow steadily and evenly distribute themselves across the entire cross-section of the wire. However, if the current is alternating current, or AC, the flow of electrons is constantly reversing direction. Whenever current changes direction, it generates a changing magnetic field inside the conductor. According to Faraday's law of induction, this changing magnetic field induces small, localized circular currents within the metal, known as eddy currents. These eddy currents are the key to the skin effect. They swirl in such a way that they oppose the main flow of current in the dead center of the wire, canceling it out, reinforce the main flow of current near the outer edge of the wire. As the frequency of the AC signal increases, the magnetic field changes faster, the eddy currents become much stronger, and the canceling effect in the center of the conductor becomes more severe. By the time you reach microwave frequencies, gigahertz range, the current in the center of the wire is essentially zero. The electrons are crowded strictly to the outer skin.
2. Theoretical depth. The mathematics of decay. The skin effect is not a hard boundary. The current doesn't simply stop at a specific depth. Instead, the current density decays exponentially as you move from the surface deeper into the conductor. The current density J at a given depth Z is described by the equation here, where J is the current density at the absolute surface. Defining skin depth delta. By definition, the skin depth delta is the physical distance from the surface at which the current density has decayed to 1 over E, roughly 36.8%, of its value at the surface. Because power is proportional to the square of the current, roughly 86% of the RF power is concentrated within just one skin depth, and 98% is contained within two skin depths. The formula to calculate the exact skin depth is derived from Maxwell's wave equations for a conductive medium shown here, where F is the frequency of the microwave signal in Hertz. Omega is angular frequency. Sigma is electrical conductivity of the metal in Siemens per meter. Mu naught is absolute magnetic permeability of the metal. Mu naught is permeability of free space. Mu r is relative permeability of the specific metal.
The theoretical takeaway. Looking at the formula, skin depth is inversely proportional to the square root of frequency, conductivity, and permeability. Higher frequency, shallower skin depth. Better conductor, shallower skin depth. Magnetic material, drastically shallower skin depth. This is why magnetic metals like nickel are generally terrible for carrying microwaves. 3. Material properties and calculations. To calculate the skin depth for copper, gold, silver, and nickel, we must use their standard material properties shown here. Use the formula here to calculate the skin depths in micrometers. Note on nickel. Nickel is ferromagnetic. At low frequencies, its relative permeability, mu r, can be around 100 to 600. At high microwave frequencies, ferromagnetic resonance causes mu r to drop significantly, sometimes approaching 1 at millimeter wave frequencies. For the sake of demonstrating how magnetic properties impact skin depth in classical calculations, the table below uses a conservative theoretical static value of mu r equals 100 for nickel. Note, 1 micron is 1 millionth of a meter. For context, a human hair is about 70 micron thick.
4. Practical engineering implications. Understanding these numbers dictates several common practices in microwave manufacturing. 1. Hollow conductors. Because the center of a wire carries zero current at microwave frequencies, we often use hollow brass or copper pipes, waveguides, or tubular coax center conductors to save weight and material cost. The RF signal literally doesn't know the center is missing. 2. Hollow conductors over copper, ENIC. Copper oxidizes easily, which ruins its conductivity. Gold does not oxidize, but as shown in the table, it is actually a worse conductor than copper. Therefore, PCB manufacturers plate a microscopic layer of gold over the copper traces. If you make the gold layer thinner than the skin depth, often around 0.05 micron, the microwave signal will actually pass through the gold and ride primarily in the highly conductive copper underneath. 3. The nickel problem. In the ENIG, electroless nickel immersion gold plating process, a layer of nickel is placed between the copper and the gold to prevent them from migrating into each other. Because nickel is magnetic, its skin depth is incredibly thin, making it highly resistant to RF. If the gold is too thin, the microwave fields penetrate into the lossy nickel layer, drastically increasing insertion loss. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.